name is Dylan. I'm a reporter for Group 1, and I'm going to be talking to you guys today about the results from last week's experiment, the clip here on. Some key points I want to go over. I kind of want to refresh y'all on the objectives and procedures from the report, from the experiment. And for those, this is for people who either didn't have the project, the experiment we had, or just for the people that did have it, just to kind of do a little refresher. And then after that, I'm going to kind of go to the apparatus, which will kind of explain each piece of equipment used in the experiment, that we can get a better understanding from when we go into the actual equation, which is kind of the theory side, and then into the analysis, which is the application of what we learned in thermo and from the lab manual. So the objectives, what we wanted to do was for a range of temperatures and pressures was to determine the latent heat of heat vaporization of water using the Larkin equation. Another thing we wanted to do was to be able to observe and analyze the relationship between pressure and temperature in the sense of boiling water. And another last thing we wanted to do was to be able to apply these thermodynamic principles that we learned in school and class beforehand, and to be able to actually perform an experiment in order to get tangible results for students to actually be able to see what they're learning, not just on paper. So some of the apparatus that we used was the boiling beads in the flask. These were important for, the glass has a smooth surface, which allows for the nucleation sites so that the water boils smoothly instead of it doesn't become superheated. This is the same thing that happens when you take a coffee cup, coffee mug, put it in the microwave, and you heat up your coffee. The inside of the mug is really smooth. So, and this happened a couple times, is people, they tend to put their coffee in there, and your coffee get really hot, but it won't boil, but it'll get to the temperature of boiling because it's so smooth, you can't actually tell it's boiling. And when people get their coffee cup out of the microwave, they hit it and it instantly cracks, and you can actually burn, kind of explode a little bit. So it's kind of the same principle. The smooth allows it to do the same kind of deal. The other thing was the vacuum pump. This was to create the low pressure inside the flasks before we could start recording data in order to boil the water. And then the hot plate was to actually heat the water to the point of boiling. And the thermocouple, type K, was to record the temperature of the water and to analyze, or to be able to take our results and the data collected, and that way we can analyze it later on. So take a look at the Larkin equation. It's given as the difference in saturation pressure over the change in temperature is equal to the enthalpy over the temperature times the specific volume. We use that later on, but in order to put it into more applicable this situation, we substitute an ideal gas equation as an approximation to kind of get more easier results, and it's easier to calculate in our kind of situation. So what we do is we replace the specific volume, PV equals nRT. So what we do is replace the specific volume with temperature, with the saturation pressure over the temperature times our ideal gas constant for water vapor. And when we integrate that, we end up getting the natural log of the two pressures that we wanted to compare is equal to the negative of the change in latent heat of vaporization over the ideal gas constant, and that's multiplied times 1 over temperature 2 subtracting temperature 1. Other ways this can be arranged is it's from other ways that I've seen other integrations is they will either switch these two pressures, or what I did in mine later on was I just put T1 subtracting T2. So to refresh from the experimental procedures for those that either didn't do the experiment, like I said before, or just to refresh the guys that did actually do it. just to kind of brief, we used the vacuum pump to bring the pressure down in the flask to close to zero, or as close as we can get it. While making the vacuum, we wanted to heat the water to the boiling point, and boil it, get it to a pressure at boiling close to zero. And then once the water is at a rolling boil, we want to cut the pump off and slowly release the bleed valve to where if you do it too fast, the water will quit boiling at the restart. So we want to slowly release the pressure out of the pump in order to keep the water boiling, so we can keep that constant rise pressure and a constant rise in temperature. One thing we wanted to make sure though was to make sure that the thermocouple is submerged but not touching the beads or the flask itself, because that can give us anomalies in our data, or it can really skew our data sets. So look at the analysis. The first thing that was kind of desired was to plot the pressure versus temperature PVT chart that we used in thermo. In the orange, we use that's the steam tables for water, and following it is what we actually had for our experimental data in the blue curve. They pretty much follow the same path with just a little bit of divergence here. So procedure one of the analysis that was requested of us was to take local derivatives along points throughout the data. We have 850 data sets. So the way that I split it up was that I would take, it started at 38 degrees, but in order to get it at an even comparison with the steam tables, that way I can get a good comparison and contrast, was that I started at 40 and went down by 5, as close to the 5 degree Celsius increments. And then of that, I would take the local derivatives. So at each temperature, we would take the difference of the temperature that we're at, the temperature before that, and then I converted the pressure that was given in PSI to kPa, and this would allow us to then substitute that equation given for us to find our vaporization of water constants. And that's the comparison with the steam tables in orange and the experimental data in blue. Procedure analysis 2, essentially, we just wanted to, it was to find a better way to fit the data to our steam table data. So what I did was I split it up into 4 piecewise functions and then used that and found the slope of each of these equations, kind of like we do in instrumentation. And that slope is also equal to dP dt. So what I did was I split it up from 40, a range of 40 degrees to 60 degrees Celsius, or 40 degrees to 55 degrees Celsius, and then use that data set as one data line. And then I did the same thing, splitting up in different increments or groups to basically use these 4 different slopes. And plotting it, it gets a little bit of a better fit, but there was a better method of doing that, which was the third method, and that was to actually use regression in Excel to do that, to find our constants, to be able to fit it. It doesn't fit entirely better, but you can get a better idea of how different the actual the latent heat of vaporization, or the enthalpy, actually compares to the steam table data. So it gives you a better sense of how it actually fits compared, because we're allowed to get a closer equation of how to quantify the change in the data. So in conclusions, the error in the experiment the error in the experiment comes from human error, where the thermocouple is actually placed, and how far it is off of the base. The first analysis procedure that we did, which was local derivatives, came out to have significant error because you're leaving a gap between 40 degrees and then your next one would be to 55 degrees. So that's a big gap of data points that aren't being represented in the calculation in the plot. So the third method proved to be more accurate because it actually allowed you to retrofit the data using regression and to get your constants to plot a better comparison curve opposed to just taking large gaps in your data sets to plot. So that's it.
Thank you, Dylan. Any questions?
Were y'all able to like mount the thermocouple somewhere, or were y'all holding them?
No, so and on the top of the flask, there was it's like a rubber seal plug, and that had a hole in the top of the thermocouple. Yeah, it's in the top. It's sitting there. Yeah,
So like, could you see where it was at?
yeah, you could. Yeah, we would set it up to where it's at. Questions?
That's all. Thank you, Dylan.